Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on group, lecture number 65, in which I will discuss second isomorphism theorem. Before discussing the second isomorphism theorem, I would like to give you basic concepts related to second isomorphism theorem. Let G be a group with given binary operation, N be a normal subgroup of G, and H be a subgroup of G. Then H intersect N is a normal subgroup of H. This is number one. Therefore, the quotient group H by H intersect N exists. Number two, Hn is a subgroup of group G. Number three, N is a normal subgroup of Hn. Therefore, the quotient group Hn by N exists. Now we state and prove the second isomorphism theorem. Statement of second isomorphism theorem. Let G be a group and H be any subgroup of G. If N is a normal subgroup of G, then the quotient group Hn by N is isomorphic to quotient group H by H intersect N. Now we prove this. Given that G be a group, H be any subgroup of G, also N is a normal subgroup of G. Therefore, H intersect N is a normal subgroup of H. Implies that the quotient group H by H intersect N exists. This is number one. Again, H is a subgroup of G and N is a normal subgroup of G. Implies that Hn is a subgroup of group G, and N is a normal subgroup of Hn. Implies that the quotient group Hn by N exists. This is number 2. I have already given these concepts in my lecture number 64. Let this is group G, H be a subgroup of G, and be normal subgroup of G, and this portion is H intersect N, and this is normal subgroup of H. Now let phi be a mapping defined on H into the quotient group Hn by N, such that phi x equal to xn. X belongs to H. This is number 3. Now we show that phi is well defined. Let x, y belong to H and x equal to y, implies that xn equal to yn, implies that phi x equal to phi y. Therefore, phi is well defined. This is number 4. Let this is subgroup H, and this is quotient group Hn by N. Phi be the mapping defined on subgroup H into quotient group Hn by N. Here, for element x belongs to H, we get image left coset xn. Now, to show that phi is a homomorphism, let x, y belong to H, implies that x operation y belong to H by closure property. Implies that phi x equal to xn, phi y equal to yn, phi xy equal to xyn. This is number 5. and phi xy equal to xyn equal to xn yn, since n is a normal subgroup. And xn equal to phi x, yn equal to phi y. This is number 6. Implies that phi is a homomorphism. This is number 7. Now to show that phi is onto let Z be an arbitrary element of Hn and Zn is a left coset, implies that Zn belongs to Hn by n. Let this is number 7. Since Z belongs to Hn, therefore Z may be written as Z equal to H1 N1 for some H1 belongs to H, N1 belongs to N. Let this is number 8. If phi is onto, then we have to show that for arbitrary element Zn belongs to Hn by n, there exists a pre-image in H. Now phi H1 equal to H1n. We may write this H1 here N1n. N1 belongs to N, implies that N1n equal to N. N is a normal subgroup, that is N is a subgroup. This equal to H1 N1 N. This equal to H1 N1 equal to Z N, using 8. Therefore, for any Zn belongs to Hn by n, here Zn, any element of Hn by n, we should have a pre-image. There exists H1 belongs to H, here H1. such that phi h1 equal to Zn. This is number 9. Therefore, phi is onto mapping. This is number 10. Hence, we get phi defined on H into Hn by n is onto homomorphism. This is number 11. Now, to find kernel of phi, car phi, kernel of phi is the collection of all those elements of H. Here, car phi. Such that phi x equal to identity element of Hn by n. Since identity element of Hn by n is n, this is equal to x belongs to H such that phi x equal to n, since n be the identity element of Hn by n, quotient group Hn by n. This equal to x belongs to H such that phi x equal to xn. This equal to n. And this is possible only when x belongs to n. Since n is a subgroup, normal subgroup, that is subgroup. Here we get x belongs to H and x belongs to n. This equal to x belongs to H intersect n. Therefore, car phi equal to H intersect n. This is 12. Since car phi, kernel of phi, is a normal subgroup of H, therefore quotient group H by car phi exists. This is number 13. This is H by car phi, kernel of phi, using 11, 13 and first isomorphism theorem. we get that there exists an isomorphism psi defined on H by car phi into Hn by n, that is H quotient group H by kernel of phi is isomorphic to quotient group Hn by n. This is psi. Implies that quotient group H by car phi equal to H intersect n in 12. H intersect n is isomorphic to quotient group Hn by n. Implies that Hn by n quotient group is isomorphic to quotient group H by H intersect n. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.